Hello again, this is Dr. James Camp from Lee College in Baytown, Texas, and this is part 2 of my commentary on Chapter 9 of Big C++ by K. Horstmann. We're talking more about classes and object-oriented programming. We're going to start with the idea of tracing objects. You've hand-traced code to understand functions. You can hand-trace objects with an index card each as well. Remember, our cash register object has an int item count and a double total price. So the back of your index card is going to have a little table with a column for item count and a column for total price. They initialize with values of 0, then we add an item that's $19.95, and so item count goes to 1 and total price goes to $19.95. And we could keep playing through more code and see what happens as we do that. In fact, here's an opportunity for you to practice that. You can take a index card for register 1 and an index card for register 2 and play through what happens in each of these lines of code here, where we buy one item on register 1 and then another item on register 2 and go back and forth. Okay. In the world of designing and implementing classes, there's sort of a 6-step process that the book recommends for implementing a class. The first is to get a list of the responsibilities of your objects. Then you write the public part of your class definition to define the public interface. You add comments documenting the public interface, and then you're ready to define the necessary data members. You implement constructors and member functions, and finally, you're ready to write a test unit program to test your class. So let's say the problem statement is to write a class for a bank account. Okay, customers can deposit and withdraw, but if the balance falls below 0, there's a $10 overdraft penalty. At the end of the month, interest is added to the account. The interest rate can vary every month. So first off, what are the informal responsibilities? We need to be able to deposit funds and withdraw funds. We've encountered those responsibilities before in other programs we've written. We need to add interest. And there's a hidden responsibility that the user wants to be able to find out how much money is in their account. So we need to be able to get the balance. So from this, we can specify the public interface. We're going to have a constructor and a constructor that allows us to set an initial balance. We're going to have a deposit and a withdraw. We're going to add interest and be able to specify the rate. And we're going to have a get balance member function. Then we document the public interface by writing this up in C++ code with function comments, the /** style comments. And now we're ready to determine the data members. Clearly, we need to store the bank balance. We need to have an overdraft penalty as a constant. Really, those are the only things we need to keep track of, unless we want to keep track of, say, the interest rate internally as part of the bank account. But the interest rate is set by the problem, is said to vary every month, so it's supplied as an argument when we call add interest. We implement our constructors, which simply set the balance. Our get balance simply returns the balance. And our deposit is going to just add a certain amount to the balance, and so forth and so on. Finally, we're ready to test the class. We create a bank account, Harry's account, with an initial balance of 1,000. We make a deposit. We make a withdrawal, which doesn't actually withdraw money. It just incurs the overdraft penalty. And then we add interest with a rate of 1%. Pretty generous interest for a bank account. And the end result is 1504.90. Okay, so how then do we decide what classes need to be in a problem? When you solve a problem using classes, you need to determine which classes to specify based on the plain English problem description. Generally speaking, if you can find a noun, that might be a class. Okay, a noun in the problem description. At least one of them will be a class. Classes usually represent data or things, not actions. Verbs then will be the member functions. Functions do things to the data, or they use the data to do things. Generally, concepts from the problem domain make good classes. So in science, you might be simulating predators and prey in a ecosystem, in which case you'd have a predator class and a prey class. In business, you might be simulating workers and their paychecks, and so you might have a worker class and a paycheck class. What might not make a good class? Well, if you can't tell from the class name what it is supposed to be or what its methods are supposed to do, then you may be off track. For example, you might be asked to write a program that prints paychecks. You could start by saying, oh, class paycheck program. Well, in Java, you'd have to have that class, but then you'd have to break it down into smaller ones. In C++, you don't need to have a class for the entire program. It's much better to come up with a class that's something more specific, so a class that represents an object in the problem description, and the object of the problem description is the paycheck itself. You can visualize a paycheck object. You can think about what's necessary for it. For example, multiplying wages times hours, or computing taxes to subtract from the paycheck. Okay. When you analyze a problem, you often find that you need multiple classes. For example, if we extended our cash register program so that, which you will do in this class, as one of your assignments, so that the cash register object actually stores individual items, okay, you might need a cash register class and an item class. Okay, the cash register would have items. Okay, it would collect or aggregate a group of items. Similarly, if we had a quiz, it would contain, aggregate, collect multiple question objects. And that would look like this. Class quiz contains a vector of question called questions. An example of a set of objects, this is in C# instead of C++, but this is an example of objects that I made for a quiz program I wrote. The quiz page itself has a page title and a page heading, and then it has a list of questions. Okay, the class question can be of type multiple choice, multiple answer, or fill in the blank. Okay, and it has a list of answers that go with the multiple choice and multiple answer types, or even fill in the blank. You can have imagine multiple correct answers for a fill in the blank question. In summary, when you want to analyze a problem description, you're going to find the concepts that you need to implement as classes, often by circling or highlighting all the nouns in the problem description. You're going to find the responsibilities of the classes to encode as member functions by circling or highlighting the verbs in a different color. And then you're going to find relationships between the classes to see if there are is a or has a relationships. Has a relationships you implement with aggregation, like we just showed. Is a relationships we'll implement with inheritance, which is the next chapter. Some practice. Suppose you're to design a software system to maintain the circulation system of a library. Okay. It has a list of library patrons, so you need a patron object. It has all the items that can be borrowed by patrons, so you need item objects, which could then be a book, a CD, or a DVD. Suppose you want to design software to maintain a collection of recipes. The recipe contains a list of ingredients, so you need to aggregate ingredient objects, and it needs a list of steps or instructions, so you need an instruction object. Okay. Another way you can use objects, and this often becomes part of another bigger object, is let's say you have item descriptions and item prices, and we were trying to make a cash register that kept track of the descriptions and prices of everything we bought so that it could print out a receipt. Parallel vectors, having one vector of descriptions and another vector of prices, get to be a pain. What's better is to make an item class, which has the description and the price as data members, and then replace the parallel vectors with a single vector, vector of item, called items. You may have figured out at this point that we can also have pointers to objects. Pointers to objects work very much like pointers to structs that we did in the previous a couple of units ago, or a couple of chapters ago. We can let Joe's account pointer point to Lisa's account pointer. We can let Lisa's account pointer equal a new bank account. We can do all of the things that we're used to doing with pointers and dynamic memory. Dynamic memory is a really handy thing to use with objects, because objects tend to take up a large amount of space in our programs. As you remember with pointers to structs, instead of writing parens star register pointer dot add item, we can just write register pointer and the arrow operator and the word add item. Every object has a built-in parameter called this that points to basically itself, to what we call the implicit parameter of the object. So if you call add item 1.95, and inside your add item you set item count plus plus and total price to total price plus price, you're implicitly using the this pointer. Okay, you can actually explicitly write the this pointer if you want to. Where it comes in handy is if, say, in your constructor method, you want to specify the total price, but total price is already used by the total price field inside your object. Well, you can say this arrow total price equals total price. And this total price is the one that belongs to the object. This total price is the one that was passed in to the constructor. Okay, a couple of object pointer. We want to dynamically allocate a string object and save the address in the pointer p. We would say string star p equals new string. Okay, we want to deallocate the object from the previous task. We would delete p. We want to dynamically allocate a string object with contents high. Okay, then we'd say p equals new string, and then pass to the string constructor the quote high. And then we want to invoke the length member function on the object. We would say p arrow operator length. Okay. Now you have a point class, which has internally int x and int y. How are we going to write the constructor? We're going to say this arrow x equals x, this arrow y equals y. Okay. Finally, there are some patterns for objects that come up over and over again, and your textbook just wants to lay some of those out for you. Keeping a total, you're going to have one data member that represents the total. You're going to have an add member function, a clear member function, and a get total member function. What if instead you want to keep a count? Well, you still have an add item, a clear, and a get count. It's just that the add is a plus plus instead of a plus equals. What if we want to collect a series of values? We have a class question, which has a vector of strings that are choices. So you would have a private vector of whatever you're trying to aggregate. Might be string objects, might be item objects, might be question objects, or answer objects, or something like that. And then managing properties of an object. This is fairly important and commonly used, is that you might have, say, a student who has an ID and a name, and you would then have getters and setters for those values. You'd have a constructor that sets both of them. You'd have getters for both name and ID. You only need a setter for name because once the student has an ID in the system, we don't want to change it. Another example is simulating objects that have distinct states. For example, you might simulate fish in an aquarium. They might be not hungry, somewhat hungry, or very hungry. If when you call fish : eat, hungry becomes not hungry. When you call fish : move, if hungry is very hungry, we go looking for food and then we call eat. Else, if hungry is less than very hungry, we just hungry plus plus. Finally, there is the possibility of describing the position of an object. Some objects move around during their lifetime, like a train might have a double distance from terminus. A a bug living on a grid might have an X and a Y position that it's keeping track of, or a row and a column on a chessboard maybe, or um, even a direction that it's pointing in currently. Um, when you model a physical object such as a cannonball, you need to track the position and the velocity in 2 or 3 dimensions. So X position, Y position, X velocity, Y velocity. All right, so that's a quick summary of how to implement objects as classes, and how to design classes, how to um, simulate the classes that you have with tracing, all of those handy dandy tools. Now that you know from part 1 lecture what an object is and how to write an object, this part 2 lecture um, should give you some perspective on how to design good objects. All right. We'll have a programming problem up for you on objects and classes up on Blackboard. So, as always, good luck and happy programming.